It's not easy for us busy geotechnical engineers to keep up on industry trends while keeping up with our engineering work. Therefore, it's our goal at the Geotechnical Engineering Podcast to help you do just that. We strive to keep our listeners informed on important industry topics and also to educate you on interesting technical topics and trends in the geotechnical world. In this episode of the Geotechnical Engineering Podcast, I'll be talking with Dr. Lemnitzer, who's an associate professor at the University of California, Irvine. We'll be talking about geotechnical education and the research that she recently did on rock-socketed pile foundations. She also provides some interesting insights about the extreme flooding that happened in Western Europe and also how engineers can help with flooding events in the future. I'm your host, Jared Green, and I'm excited to bring you yet another episode of the Geotechnical Engineering Podcast. And with that, let's jump right into today's episode. And welcome to the show. It's great to have you here with us. How are you doing?
Thank you so much. I am doing fine, and I'm excited to be here.
Excellent, excellent. Well, I would love it if you could tell our listeners a little bit more about yourself and what is it that you do on a daily basis?
So I am a professor in the area of geotechnical engineering at the University of California in Irvine. And since UC Irvine does not officially have a geotechnical program, I am the one running it. So it stands and it falls with me. But I've enjoyed it very much because I was able to build a very nice curriculum. And I was able to have a very good relationship with the professional geotechnical community in Orange County, which is huge. And so my job is to educate undergraduate and graduate students at UC Irvine. I also do have a research group that consists on average of 4 to 5 Ph.D. students. Sometimes we do have 1 or 2 postdocs in the mix, and we also have undergraduate students that are interested in research and helping out. And so on a daily basis, it's probably these components that determine the schedule. So it would be teaching the classes if it's in a quarter that I'm teaching, meeting with the students that need help and guidance on the research projects, or just talking with each other. I spend typically a substantial amount of time in the lab because my research work is primarily experimental, large-scale experimental. And so I work alongside my students doing everything from, rooming the floor to installing strain gauges to installing hydraulic actuators and pushing piles to failure. But it's good. It's a very close family type of relationship, but it's very rewarding. And then I do have a substantial amount of time during the day, which I should probably reduce, but on service work and on professional work. And but that involvement has been very good for me and also for the geotechnical program at UC Irvine, just the connection to the societies out there.
Awesome. That's awesome. I have to imagine that to think of yourself as a department of one, it's got to be intimidating when you first start, but that's
Yes.
pretty awesome. It's pretty awesome.
I have to say, during the tenure track, it was very intimidating because you want to make that work, and then you also have the pressure of trying to produce something critical and making tenure and maintaining a group. So it was a little challenging, but I think now I got the hang of it.
Excellent.
So it's really enjoyable.
Excellent. I'm sure it's going to be helpful for our listeners. We have a number of listeners that are working on their pathway towards the PhD. We have some that are young professors. It's like, how do you do this, right? There's no manual, so to say, for how to do it. So
our goal is to add more geotechnical faculty, to the program. So yes, that Excellent. Is a future goal. And if we do have valid candidates, I would be happy if we can start to have pushing and starting the conversation with the dean and get more people on board.
That's exciting.
Because Orange County is the area in Southern California that I believe has the largest representation of geotechnical companies, over 230 companies.
Wow.
And the county is not
That's a lot.
Yes. It's a lot. Yes. It's a very high concentration. So.
Got it. I'd love if you could shed some light on student enrollments. From what I understand, when you look at student enrollments for geotechnical programs, seems like it's kind of low compared to other engineering disciplines. Why do you think that is? Or actually, do you think, is that true what I'm saying? And if so, why do you think that is?
It is on average true. Speaking for the universities in the University of California system and also outside. And I believe a lot of it has to do with the perception. And multiple studies have shown that this to be true. It started, for instance, when was it? I think it was in 1991 in the Journal of Education, the first study on the perception of various engineering disciplines. And I'm going to quote, geotechnical professionals are often perceived as unsophisticated, awkward in public, poor communicators, and without any outside interests. I wonder how some of us get married, but
Wow,
that's a different story. So that was in 91, and then there was another study in 2005 that almost confirmed the same, and in 2017, and it is a perception. It is not sexy to have something that's always underground. You don't see it. You don't see that cool, glossy looking skyscraper that everyone can say, oh, I was part of this construction. And so students don't perceive it as having the same value and the same prestige. And, you know, and even geotechnical engineers themselves don't. And so we did, in the last 2 years, we did a survey within the Earth Retaining Structures Committee of ASCE. And in that survey, we did some industry and some academic questionnaires. And as part of the survey, at the very end, we asked, how do you think other engineers or other professionals rate the importance of geotechnical engineering in comparison to other fields in civil engineering? And 51.4% answered either less important or not really important at all. And so that's what geotechnical engineers thought, because that survey was only among geotechnical engineers, primarily in the foundation area, what they think others think of them. And then we asked, well, where does that come? What are the stereotypes that you think exist out there? And the top answer, which I don't think is true based on statistics, was with 58% that it's lower salaries. But I don't think that's the main driver, unless the national statistics don't, take more recent salary escalations in like construction management or transportation engineering into account, or it averages out somehow. But then the 55% said the work was not as interesting as above ground construction, but unattractive because it's playing with dirt was 45%, and 36% was the work done by geotechs can be performed by structural engineers. And that was surprising. And it made me think, is what are we doing wrong as geotechnical engineers and as geotechnical educators to not install that sense of pride and that sense of ownership and that sense of we are the ones that lay the foundation for everything that you see. And without us, this thing would not be standing.
Right.
And maybe I think we do need to be more passionate about in our communities, in our outreach and towards our students to install that curiosity for geotechnical engineering. Because I don't think it is the salaries, it is really still the cultural and professional perception.
Wow. So we've got our work cut out for us then,
Definitely.
Wow.
And when I prepared my career proposal for NSF and I did all the background research on outreach and all sort of stuff, I read a study that but that was specific to female professors in geotechnical engineering. But in general, it said that the retention rate in the field of geotechnical engineering of female professors was only 10%. So people enter and then they either leave or they don't make it. I don't want to say they don't make it because we don't know the reasons why, but then, if we, not necessarily for all, but if we don't have the role models, then where is the next generation is going to get their inspiration from? That was specific to like females in geotechnical engineering, but I think it applies to everything else as well.
Yeah. Wow. So it's almost like there's a public awareness campaign that has to happen in a sense, because, even some of the descriptors you said about like geotechs not having a life, I'm just thinking about just the conversation we've had on the podcast. It's like, talk to some very interesting people, yourself included, which we're going to get into, just what people are doing outside of geotechnical engineering, what people are doing with their degree in geotech. And it seems like, there's still a lot of potential for folks to have very rewarding careers within the realm of geotechnical engineering. So we got our work to do as far as continuing to share what it is we're doing, so it's attractive for people.
Yeah, totally agree with that.
Wow. So as a part of that, we think the grad school is definitely important for engineers. And a lot of times people ask me, like, I hire people that are undergrads, hire people that have a bachelor's degree. And sometimes people ask, well, is it necessary to go to grad school? Now, of course, you're going to be biased because you're a professor, but please sell it. Like, what is it important? If it is important, why is it important? Why is it necessary? What are your thoughts on that?
Well, obviously, I am speaking from a perspective of someone who went all the way through graduate school until the very bitter end. And I do not say that everyone should go that route, obviously, right? But I think going until a master's degree has become essential today. And I tell that my students too. And I think it's essential for two things. One is the technical skills, and that is something, sorry, I'm going to be a little bit criticizing the US college system.
Sorry.
But in comparison to many universities in the rest of the world, in the United States, we spent the first 2 years reteaching fundamental math, physics, and chemistry in GE level courses that 90% of other kids in the world learn at a high school level. Like solving differential equations is typically 11th grade topic. You don't have to put that in the first year. And there's nothing we can change about that right now, in the school system, because that's just how it's set up for each country. And so it's very difficult to change. And I recognize there are other AP level classes out there where it's more comparable. But so until they really get into engineering, it's the third year of their education. And then they have only year 3 and year 4. And what do you learn and what do you know after 2 years of engineering education? I would be scared to drive on a bridge designed by one of those. Not saying that, but let's say by a freshly graduated student.
All by themselves, yes.
Yes, but I mean, we can't even blame them. It's not their fault. Yeah. So for the reason of to be more specialized, to have more expertise, because construction is not going to get less complex, and loading combinations and natural hazards are not going to get any less. So these are things that simply can't be learned in any undergraduate education anymore. But I also perceive another factor as critical in graduate education, and I think it's the personal development. And it has to do with it being much more difficult, with it being more targeted, being more competitive, and it forces you to prove endurance, patience, persistence, sustain or like survive in a rigorous and competitive environment, and try to be on the top, because a B- in graduate school is semi-considered almost fail unless you can really well balance it out with a lot of A's on other classes, right? Mm-hmm. And so but not only that, I mean, it also teaches more problem solving skills and critical thinking. Mm-hmm. And I think that's appreciated by an employer. And so I tell most students that don't wait, but that's just my personal opinion. Mm-hmm. I think it is the easiest to add a master's degree immediately after the bachelor's degree. You will never be as fresh and as dedicated and as undistracted in your life than in that moment. And students don't believe me that. They say, oh no, we want to go, and this undergrad was so hard and we need a break to find ourselves for 1 year by traveling around. Like, okay, who had that luxury, 50 years ago? Seriously? So do it while you're fresh and you have the energy. And that survey that I told you about with the ERS, where we ended up adding some general level questions, we asked the companies at which level they hire the most. And I need to cheat here really quick, but 56% of the companies said master's level.
Yeah.
And then 15% said PhD, and about 38 said bachelor's.
Okay.
And when we asked them if they think there is a lack of geotechnical engineers or professionals in the workforce, 61% said there is.
Wow.
And we asked them to fill in the answers, and they said some of them said, we have spent an entire year now looking for a qualified geotechnical young engineer. Wow, and then I'm thinking, wow, we do have some work to do.
Yeah. We've got work to do, and then there are opportunities for those, those that are listening right now studying geotechnical engineering. Yeah. It sounds like the odds are in their favor to get a good job.
Yes, definitely. The demand is out there, and companies are happy to invest and develop, and provide career opportunities. Yes, definitely.
Yeah. That makes a lot of sense. Yeah, I ended up doing my master's right after undergrad. I said, I just want to get it done now while I'm fresh. I like that we said it before you're distracted with life,
It is.
Yeah. But I guess it does come down to opportunities, sometimes,
yes,
can't get a fellowship or, research opportunity isn't present. But I think it's really hard to go far in geotech without that master's. So I would echo what you're saying there.
And I have, when I did my master's, it was at Cal State Long Beach, my first one. It is a class where all the graduate level classes are taught primarily in the evening, so that professionals could attend.
Got it.
And, there were a lot of professionals attending, but based on the family demands, the work demands, the daily schedules, more than one class a week with 3 hours per night and homework and exam studying, there's no work-life balance or nothing anymore. So it is hard.
That's true. There's a lot to think about. I'm glad it's behind me. Glad it's behind me now.
Yes.
But it's preparation. I guess it's preparation for life when we think about what the daily life looks like now, right? There's just so many things that have to get done. Wow. But switching gears a little bit, let's talk a little bit about research. And I know you've done research on rock-socketed pile foundations. So for the listeners that might not be familiar with that type of pile type or pile installation, tell us a little bit more about that.
Okay. So my research in general is predominantly in the area of deep foundation engineering and soil structure interaction, even though I have ton of other projects within SSI going on as well. But I am very interested in the behavior and the performance of pile foundations. And rock socketed foundations are unique in the sense that you install the pile, and primarily, what we call it in California, the drill shaft. In Europe, that's not so common. It's called a bored pile still, into the bedrock. And taking advantage of the high strength and the high stiffness of the rock material. Well, I have to recognize, yes, there are weak and weathered rock zones that make us, throw us some challenges along the way in terms of the design process. But rock-socketed piles do have that benefit of taking advantage of that strong rock component at the very bottom. And what we have specifically studied within the large set of experimental tests is when rock-socketed piles, for instance, motivated by case studies in the Bay Area, or where you have very soft surface layers that just consist of bay mud or other soft or loose sandy type of materials, that they have to pass that layer and then they have to go into the rock. And there is a phenomena for those piles that when they are subject to lateral loading, such as an earthquake or wind loading or other lateral impact loading, when you use the typical or most commonly used Winkler type foundation analysis method, like the PY method, what it says that, or what the results that you get is a shear spike. So to explain it in layman terms, we represent the soil by the springs, the PY springs, and they represent the soil stiffness. So I would have very weak springs for my upper surface layers. I would have very stiff springs for my rock. And every single time my pile passes one of those very strong stiffness contrasts, as a result of that mathematical derivation that we all had in our undergrad, the beam equation where we go from deformation to the slope and then to the moment and times EI, and then we get the shear and then the force or the pressure P. Yes, so what happens when you go from a soft to a very stiff surface soils, we're gonna get a spike in the shear force. And that has thrown geotechnical designers a curve, because that amplification around the rock socket boundaries is typically per design, or it can be up to 8 or 10 times as high as the applied shear force. And so contractors see these huge rebar cages coming to the field with super densely installed transverse reinforcement, and is their biggest nightmare, because they know once we install that inside a rock socket, how is the concrete going to flow through it? And it causes huge constructability issues and huge liability issues on the site. And so our interest was to study experimentally, are these shear forces real, or are they not? Are they just an artifact of the mathematical derivation in our design and analysis approach? And so we rebuilt some piles, and yes, and we installed them in a big test pit at UC Irvine. We subjected them to lateral loading with hydraulic cylinders, and we tested them until they were completely failed. And specifically for that, we also developed a new type of sensor. It's kind of a prototype that we tried out and are currently publishing, but it is a sensor where we tried to measure the 3D state of strain within a pile, so we can almost indirectly, but still somewhat empirically, determine the shear stress in the pile. And what we observed is that this artifact of this huge shear magnification that causes so much challenge to the designer and the contractor when the pile passes through those stiffness contracts was not real, at least not in that magnitude that it was predicted. We noticed maybe you apply 5 kips at the top and you may be getting 8 or 9 kips near the rock socket. But what the PY analysis sometimes would just suggest, you apply, I don't know, 2 kips at the top and you get 15 down there, And so that was my most recent research endeavor. And so together with a ton of instrumentation, the simulated earthquake loading, we reached the conclusion that we finally have some experimental data that prove, and they are a relief to many designers and contractors, that these huge magnifications are not real. Plus, we have the rock socket there anyway, right? It's going to take and absorb some forces regardless. So why is no one taking in account the confinement that you have? And so our ultimate goal with that is, so right now we tested 3 piles. We're planning to test 3 more, and then do a whole load of numerical sensitivity studies and parametric evaluations. And then once we have enough cases using finite element analyses, and once we have that, our ultimate objective is to develop some design charts and guidance that people can use to kind of get a more realistic feeling of what is really there in terms of internal demands.
Awesome. That's awesome. I mean, just hearing that, honestly, I don't know how somebody couldn't be excited about geotechnical engineering. Like that's changing the industry, right? It's like when you
Yeah,
fast forward, that changes
yeah,
how we design the elements, how we construct the elements, what those materials look like, what the material cost is, the carbon footprint, the embodied carbon. I mean, there's a lot
yeah,
that
yeah,
happens there. So that's awesome. That's awesome.
yeah. You're right. Over design is pretty much a huge taxpayer burden, right? And if you
It
do
is.
this for hundreds of piles, it's like a irresponsibility on our end on what we do with taxpayer money. And the interesting thing is that the original idea or some part of the idea actually stems from the DFI drill shaft committee and the conversations we had in there. And then we took it a level further, and the National Science Foundation recognized this as such a fundamental but influential issue that we received funding from both entities for the study,
That's
which
great.
I think is very cool. Plus, maybe we can develop some more sensors that would help to solve some other similar problems.
Yeah. No, that's great. That's great. Well, I was going to ask you a little bit more about, rock socketed piles and how they behave and what are some of the things from a design and construction, what are some of the challenges that engineers face? You touched on some of those with the artificial spike and the shear as you go down the shaft. But what are some other things that folks should be thinking about?
Well, I think from a contractor's perspective, it's always the quality assurance when you install,
Mhm.
because the rock quality is never fully known. Like in our experiments, we assumed it to be perfect rock, but when do you ever have a perfect rock, right? We simulated it with high strength concrete. But a real challenge is how do you represent weathering and weak rock within the first maybe upper foot or maybe 2 or 3 foot. The next thing is when you start drilling down there, you're breaking off and breaking out some of the rock depending on whether it's weathered or not. And it is from a constructability issue. Yeah, that is a huge challenge to contractors and engineers alike. How do you account for the existing confinement of the rock that is there? Some don't want to put any reinforcement in any rock socket. And I could understand this if there is enough and you have a very well intact rock, then maybe just to have enough transverse steel there that holds your longitudinal rebar cage together would be sufficient because the confinement is there and the contact is there. What are other challenges? I think there are more challenges in areas where you have more complex loading like seismic loading. I believe for axial pile design, we are pretty well ahead
Yeah,
of the
that makes sense.
game.
Mhm.
Especially now with rock coring and rock drilling. And, if you get some good samples, we can get a relatively confident design going for those piles. Seismic, lateral loading, those type of things, yes, they will remain a challenge, and how to really represent them. I have recently seen some interesting developments on how to represent the load transfer within rock socketed piles using the structurally motivated strut and tie model. And that has shown, very reasonable results, a very good representation of load being transferred using the compression and tension struts until your load axial, both axial and lateral, reaches bedrock. So I believe Ben and John Turner were one of the people that took the lead on that, and I'm pretty sure we'll see some more publications coming out on that.
Oh, all right, great, great. Well, if we, I guess, switch gears again, I know that you recently traveled to Western Europe where you did some observations on the extreme flooding that unfortunately killed over 230 people. What are some of the things that you note in regard to geotechnical failure and impact on infrastructure that you share with the listeners?
Yeah. So the Western European floods, they occurred in July 14 through 16 of 2021. And they were primarily driven by very strong precipitation, some of which was anticipated. Some of it was also known to the fullest extent until short before, just no one believed the numbers that they were predicted. Early warning systems did work, but not everyone either followed, and also the severity of the flood was not well emphasized enough. So that's why we ended up with 230 deaths in countries that have extremely high developed infrastructure, right? They both occurred in Germany and in Belgium. The Netherlands and Luxembourg were also affected, but there were no fatalities there. And so we mobilized a team from GEAR. I had a co-lead, Professor Nina Stark from Virginia Tech. She's also German. And so they used the two German geotechs from the US to, to navigate the muddy waters past the flood. And we took a team with us. In the end, we ended up having a team of 17 people internationally, with local and US and Dutch and Belgium representation. And we visited first the various areas that you might have seen in the news, where, for instance, this huge gravel pit that filled with water and ended up sucking entire agricultural fields and part of towns into the gravel pit as it filled with water. The area was known as a floodplain, but there was nothing you can do with this extent. And then the pictures afterwards, they show crater type of, it almost looks like the Grand Canyon. And I can provide you some of the material like that, so our listeners have an idea of what we're talking about, like this, just the severity of it. So that was one of the hotspots that we visited, and it was also nationally broadcasted. And then besides multiple other regions, I think the one that stands out predominantly is the valley of the River R. And in there, it really looked like a war zone. It is a very small river. Imagine the width in its normal flow bed, maybe between 2 and 3 meters. It's depth 60 centimeters, 2 feet, maybe 2.5 feet. During the flood, it raised from 60 centimeters in some locations to 11 meters. So that is 30 plus, 33, 35 plus feet.
Wow.
Okay. And the river turned into just a raging flow of water. We have valleys on, like it is a valley, so we have the slope of the mountains on both sides. Some had vineyard, others was just rocky type of hilly landscape. The soil was almost nearly saturated at the time where that major, low pressure system hit the area. And the first thing that happened is, well, we saw tons of cars, tons of caravans, tons of trees being ripped out. They were all transported. They crashed into infrastructure components such as bridges. They blocked the cross-sectional area for the water to flow through. There was no clearance, nothing left. And so it ended up, triggering failures of the bridges. It ended up triggering flood or wave-like tsunami type of flow waves going downstream, and that just accumulated over 60 kilometers. And so that was one of the main damage drivers. When we were there, people described to us entire trees being ripped out, the logs crashing into houses. They said it sounds like bombs hitting, like explosions in the middle of the night. For the historic bridges that we visited, we noticed a lot of scour failure. We also noticed that a lot of the historic bridges were on shallow foundations. And that was true for almost all the historic bridges that failed. So if they were still existing, the bridge piers and abutment walls were all tilted and rotated into the soil if they are still there. We also observed a lot of erosion and resedimentation around the riverbeds. Please note that we were there, we were not allowed within 4 weeks of the main event in there because they couldn't find all the people that were lost and died during the flood. So they were still covered in the same mud in areas that, we wanted to investigate later on. So we arranged for some time there in between. And there was a substantial amount of bridge failure. There was a substantial amount of road and highway failure, more than 60 kilometers. I believe the total loss or the total damage is now accumulating to over $17 billion, US dollars. People thought it's just going to be another 100-year event. And in the last 100-year event, which was 5 years ago, the water level rose from maybe 60 centimeters to 3 meters. Mm-hmm. And people were prepared, and some, sought refuge in higher elevations in other houses. But this was something beyond the scale that anyone imagined. We also saw a lot of houses just being lifted up and carried away, where we were wondering, and it was primarily for houses that followed a module type of constructions, where you have a pre-design and then you purchase like the design and the construction that comes with it, right?
Yeah.
It's very common in Europe. I'm not sure if it's the same common in the US.
Some areas.
Yeah. So there we noticed one of the weakness really was the connection between the foundation mat, like the slab, and the superstructure.
Got it.
So it was really a foundation problem lifting this up.
Yeah.
For the bridges, yes, that foundation, and also all the abutments were the water.
Scour, right?
Scoured out, flushed, all the soil behind it was eroded. And then a very common failure scenario was the last segment of the bridge deck completely collapsing, and that makes the bridge pretty much useless.
Yeah.
A lot of exposed utility networks, utility lines. So that's gonna take several more years to repair. So emergency lines have been prepared, right? But all the wastewater facilities that have been flooded, that's a huge endeavor to repair and to get that under control. And one more thing that we observed, and I think we don't design for that very well, at least not in Europe here, it is the connection that, like, imagine you have your abutment wall, and then you have this almost like this area of riprap, which could have various levels of strength or stability. It could be stones, blocks, cemented, or it could just be gravel or so.
Yeah.
But it was almost that area in every scenario that was first washed away. And then it was so easy to just go underneath the abutment or the foundation structure.
Wow.
So that transition zone between the structural or the superstructure element and the soil, especially for shallow footings, that was one of the major weak points.
Wow. There's a lot of things there that, because I'm thinking, as engineers, what can we do to help prevent floods like this, right? And how can we minimize the damage that's caused by floods? So a lot of these kind of weak points or areas where, these concentrated areas where weakness came about, I think those are definitely things we can address on the design side. But what are some other things we can think about as engineers?
When we were there talking with many of the officials there, with the military, with the developers and on-site responders, from engineering and from a humanitarian perspective, both. In this specific area, there's very little you can do except for avoid building in floodplains. In officially recognized floodplains, especially when you have very narrow valleys that are known for flooding. Part of that R valley has no insurance anymore because insurance companies, after it happened the last few times, are not willing to insure any buildings and any construction anymore. And yes, there is no structure or no barrier that you can build high enough to prevent this extreme, devastation. A few things that could be done. We talked with a lot of people, a better river and management, especially with regards to trees, and rotten trees that are along the riverbed that were not maybe maintained well enough, that were just so easily ripped out and carried away by the flood, and that caused the primary damage to structures. We would see that, and I'm thinking right now, but no, in terms of constructing something or a structural type is very not suitable. There wouldn't be, I mean, imagine like a
it's like what
like a 11-meter high wall
a
on both
massive
sides.
wall, right?
It's not gonna work. It's not
Yeah.
like we can build this like the tsunami wall, like in some regions of Japan.
Yeah.
Maybe I could see it there, but like they can close their entire tourism if they were to do that.
Yeah. Wow. Well, thank you for that. Thank you for that. Before we take our break, what's the final piece of advice you would give to, younger listeners that are hearing what we talked about? Some advice you'd say for, if you say to your younger self, right, early in your career, what are some things you'd come to mind?
For a young professor, thinking back on my career, maybe a young female professor, I would say, check whether you suffer from the imposter syndrome and address it right away.
Yeah.
It's very, very common, and it's so hindering, and it's almost sometimes blocking from doing great things that we're capable of doing. But that was something unique to me, but I know I'm not alone there. It's a very common phenomena amongst young engineers, and especially amongst young female engineers. The other piece of advice is, I don't know, what worked well for me is work really hard, take nothing for granted. Don't even consider the word or the what we would call entitlement. It is something that is increasingly growing, I feel, in our society. Maybe some is forced, but some is just there. But the virtues such as hard work and endurance and humility go a long way, especially in the beginning of your career. It's good to make friends and stay humble and work yourself up. That's still the only way, I would say, to success. A very quick success typically doesn't last very long, and it's also never something positive for your personal character.
Absolutely right. Well, thank you. That's a good note to end on. We're going to come right back in a minute and close this one out with Dr. Ann Lemnitzer and our Career Factor Safety In segment. Stick around. Welcome back. It's time for our Career Factor Safety In segment. In geotechnical engineering, just like many disciplines of engineering, it's important to incorporate a factor of safety into your design. But what about incorporating a factor of safety into your career? Today, of course, we're speaking with Dr. Ann Lemnitzer. And you've already had a very successful career. When you look back at your career, what's one thing you implemented in your career to give yourself a factor of safety in your career?
Jared, this is a very good question, and I have to poorly admit that I don't think I was one of these people that knew the concept of factor of safety. Maybe I only added load factors to all the drama that could happen, but not enough resistance factors,
Okay.
what could not. I added one factor of safety early on in my tenure because I was so afraid that I wouldn't make tenure. I went out and I got a bartending license.
Wow.
Probably not what you want to hear and not what I recommend to any other engineer.
Whatever it takes.
I am not going to make tenure. I'm going to at least really good tasting or well tasting cocktails. And so I did go and get that national bartending license in my first year of tenure because I was so afraid. I didn't need it. But it is always good to have, and I have profited from these skills in a lot of parties. But I can tell you, I think, no, I didn't have a lot of factors of safety because I really wanted a career in academia and I wanted to make that work. My parents did have their own structural engineering company. So in a weak moment with colleagues from Chile, we ended up opening a private consulting company on the site in South America. It was the first company to introduce CPT testing in the country of Chile. on a commercial basis. And it was very cool, very exciting, and very nerve-wracking. I have in total now 3 wonderful business partners, and we built our own CPT trucks and we shipped them from Long Beach, California to Santiago, Chile. And we held a ton of seminars, invited speakers like Peter Robertson and others to educate and to introduce the CPT testing method and to make it a more popular and relying testing method. And so it was a lot of hard work, but I always thought, if the tenure doesn't work out, then I could, South America sounds like a really attractive solution to me. So that was a little backup besides my parents' little company. But for all those who know they have like an entrepreneurial and adventurous side and skill, then, capitalize on it. Even if it's just something small, you never know what it's going to develop into. So
that's great. Thank you so much. That's awesome. That's awesome. Well, Ann, thank you so much for coming on and sharing all the great insights you shared. The information you shared, I know it's going to be great advice for our listeners. I know it was helpful for me. If listeners want to reach out to you, what's the best way for them to find you? On social media or an email you want to share?
Yes, my work email is lemnitz@uci.edu, but if you type my name into Google, it will direct you either to my website or to the University of California's website, where you can easily reach out and get a hold of me.
Excellent. Excellent. We'll make sure that we have that in the show notes. Thank you so much for coming on. Okay. This was great.
All righty. Thanks for having me.
I hope you enjoyed the episode today. We would love to hear your feedback, comments, and/or questions. Please feel free to go to geotechnicalengineeringpodcast.com, where you'll find a summary of the key points discussed in today's episode, that being episode 45, as well as links to any of the resources, websites, or books mentioned during this episode. Until next time, we wish you the very best in all your geotechnical engineering endeavors. Peace.